Today, we are tackling one of the biggest moments in the history of science, Galileo's idea of inertia. Now, it's a concept that's so basic to us now that we just take it for granted. But to really understand its genius, we first have to travel back in time and overturn 2,000 years of what everyone thought was just common sense. So get this, for 2 entire millennia, pretty much the smartest people on Earth were completely, fundamentally wrong about something as simple as why a ball rolls. I mean, how does that even happen? Well, to figure it out, we need to rewind the clock way back. You see, to really appreciate Galileo's breakthrough, you first have to understand the giant, ancient idea that he was up against. It was a concept that seemed so obvious, so intuitive, that practically nobody even thought to question it. And that man was the Greek philosopher Aristotle. Look, it's hard to overstate his influence. When Aristotle talked about how the world worked, his word was basically treated as law. And for the next couple of thousand years, everybody just went along with his very simple idea about motion. Aristotle's theory was, beautifully simple. To keep something moving, you have to keep pushing it. Simple as that. He said an object's natural, preferred state is just to be still, at rest. And this idea felt so right because it perfectly matched what we see every single day. I mean, think about pushing a heavy box, right? The second you stop pushing, it just grinds to a halt. It makes perfect sense. But as we're about to see, what feels like common sense can sometimes be dead wrong. And that brings us to our hero. The man who looked at 2,000 years of rock-solid belief and said, I'm not so sure. Galileo Galilei. He was this brilliant Italian astronomer and physicist who had let's call it a revolutionary habit. He actually looked at the world with his own 2 eyes and trusted what he saw over what he read in some ancient book. He wasn't happy to just accept what Aristotle said was true. He wanted to test it for himself. And this quote, it just says it all, doesn't it? He was just endlessly curious, and he was humble enough to think that wisdom could come from anywhere. This open-mindedness, you could say, was his secret weapon. It's what allowed him to spot the tiny crack in an idea that everyone else thought was a solid brick wall. So how in the world do you prove Aristotle wrong? I mean, you can't just wave a magic wand and get rid of friction in the real world. So Galileo used a tool that was way more powerful, his own imagination. He created what we call a thought experiment, using pure logic to see what a perfect world would look like, and in doing so, he uncovered the real secret of motion. Okay, so let's walk through this together, because it's just brilliant. Picture a ball rolling down ramp A. When it goes up ramp B on the other side, it tries to get back to the same height where it started. Makes sense. Now look at step 2. If we make ramp B less steep, the ball has to travel a lot farther to reach that same height, right? So, following that logic, here's the game-changing question. What happens if you make ramp B totally, completely flat? And boom, there it is, the light bulb moment. If the second ramp is perfectly flat, the ball can never get back to its original height. So in a perfect world with no friction, what would it do? It would just keep on rolling and rolling forever. It doesn't need a constant push to keep it going. Its natural state wasn't to be at rest. Its natural state was to just keep on doing what it was already doing. With that one single, beautiful thought experiment, Galileo completely shattered a 2,000-year-old idea. He had just discovered one of the most fundamental principles of our entire universe, the law of inertia. So what is inertia? Well, it's really just an object's resistance to changing what it's doing. It's kind of like stubbornness. If it's moving, it wants to keep moving. If it's sitting still, it wants to stay sitting still. The only thing that changes that is some outside force, like the friction that confused Aristotle, or maybe just a nudge from your hand. And honestly, you feel inertia all the time. When a car suddenly takes off, your body wants to stay put, so you feel like you're being thrown back into your seat. That's inertia. When you shake a wet towel, the towel stops, but the little water droplets, their inertia makes them keep going right off the towel. It's everywhere, from a hockey puck gliding across the ice to a satellite just coasting through space. But this discovery was so much more than just a new rule for a physics class. Galileo's idea of inertia fundamentally changed how humanity understood its place in the cosmos. I mean, it changed everything. You can really see it here. Galileo was the critical bridge connecting the ancient world of Aristotle to the modern world of physics. You see, without Galileo's concept of inertia, Sir Isaac Newton could never have come up with his legendary 3 laws of motion. And those laws, they were the bedrock of physics for centuries. So, in the end, this wasn't just some small correction. It was a complete shift in how we see reality. All of a sudden, planets could orbit the sun without needing some constant, invisible push to keep them going. For the first time, it looked like the universe wasn't some mysterious, magical place, but one that operated on clear, predictable laws that we could actually figure out. Galileo taught us that we have to be brave enough to question the things that seem the most obvious. And that courage changed the course of history. So it really leaves you with one last question, doesn't it? What common sense ideas of our own time are just waiting for the next Galileo to come along and prove them wrong?
All right, we are about to go on an incredible journey. We're talking 2,000 years of thinking and discovery, all to wrap our heads around something we see every single day, something so fundamental we barely even notice it: motion. How do things move? And maybe more importantly, why do they stop? Let's start with the one question that had humanity totally stumped for almost 2 millennia.
You know, it's a question a little kid could ask. If you roll a ball across the floor, what happens? It slows down and eventually stops. If you slide a book across a table, it only moves as long as you're pushing it. Why? What is actually going on here?
For the longest time, a really long time, the answer seemed pretty obvious, and it was championed by one of the greatest thinkers of the ancient world, Aristotle. His ideas were so powerful, so intuitive, they just became the undisputed truth.
Aristotle's logic just felt right, didn't it? It was common sense. He basically argued that the natural state for any object is to be at rest. It wants to be still. So to get it moving, and to keep it moving, you have to apply a constant force. The second you stop pushing that big, heavy box, it stops. Simple as that. Or so it seemed.
Just let that sink in for a minute. For almost 2,000 years, this one single idea was the bedrock of physics. Why? Because it just matched what people saw with their own 2 eyes every single day.
But here's the thing about science. It's all about questioning common sense. What if the reason things stop moving isn't because they want to be at rest? What if something invisible is actively stopping them? This one question, well, it was the spark that started a revolution in thought.
And this is where the entire game changed. The old view? Motion needs a constant push. But this radical new idea flipped that on its head. It said, what if an object is perfectly happy to just keep moving at a steady speed in a straight line forever? From this new perspective, you don't need a force to keep something moving. You only need a force to change its motion, to speed it up, slow it down, or make it turn.
This new idea got a name: the law of inertia. So that outside force that's stopping the ball on the floor, that's friction. The force that stops the book on the table? Yep, friction again. Get rid of that friction, say in the vacuum of space, far from gravity, and if you throw a baseball, it will just keep going and going forever.
But inertia wasn't the end of the story. Oh no, it was the key. It was the key that unlocked the door for one of history's absolute giants to walk through and build a complete system for explaining how pretty much the whole universe works. I'm talking, of course, about Isaac Newton.
See, Newton's genius was to take this idea of inertia and build a whole toolkit around it. He took inertia and called it his first law. Then he added 2 more, creating this beautifully simple yet incredibly powerful system that could predict the movement of everything from a falling apple to the planets in the heavens.
So, Newton's first law is just inertia. A really simple way to think about it is that objects are kinda lazy, or maybe stubborn is a better word. They just want to keep doing whatever they're already doing. If you've ever played air hockey and seen that puck just glide effortlessly across the table, you've seen Newton's first law in real life. Okay, so if the first law tells us you need a force to change an object's motion, the second law answers the next obvious question. How much of a change do you get for a certain amount of push? And this is where the beautiful, elegant math comes in. It's the relationship between force, mass, and acceleration.
That famous equation, F equals ma, it really just boils down to a pretty simple idea. Accelerating something really heavy, like a car, takes a whole lot more force than accelerating something light, like a baseball. And this one single rule governs, well, everything that moves.
Newton's third and final law pulls back the curtain on a hidden symmetry in the universe. Now, this is the one that everybody can quote, but what does equal and opposite reaction actually mean? It means that forces are never lonely. They always come in pairs. If you push on a wall, that wall is pushing back on you with the exact same amount of force.
The perfect example of this is a rocket launching into space. It's not pushing against the ground. It's throwing hot gas downwards with an incredible amount of force. That's the action. And in response, that gas pushes the rocket upwards with an equal and opposite force. That's the reaction. And that's what sends it soaring into the cosmos.
You know, Newton himself knew he wasn't figuring this all out in a vacuum. This famous quote is him saying, "Look, I could only do this because of the amazing thinkers who came before me, the ones who first dared to question Aristotle and came up with this brilliant idea of inertia."
So that's the world Newton gave us. But come on, that was over 300 years ago. We live in an age of quantum computers and AI. Why do these ancient laws still matter so much?
The answer is because they are the invisible blueprint of our entire modern world. I mean, from the engineering that keeps a bridge standing to the precise calculation of a satellite's orbit, even just playing a simple game of pool, you are seeing Newton's laws in action. Whether you realize it or not, they are everywhere.
And really, that's the amazing takeaway here. It all started with a simple question about why a rolling cart stops. And that question sparked a 2,000-year journey of ideas that ultimately gave us the tools to understand the cosmos and to build the incredible technological world that we all live in today.
Now, Newton's laws, they work almost perfectly for our world, but they do have their limits. When things get incredibly fast, I'm talking approaching the speed of light, or when they get unimaginably massive, things start to get, well, weird. And answering that question, that would require a whole new revolution and a whole new giant. But that, my friends, is a story for another time.